Yeah, thank you for those nice words and the history, a little bit of history of OpenAirInterface. So I joined a bit later. I joined when this my first project was on this CB MIMO card. And Christian was actually the person who hired me back at the time. So I'm also very indebted to him. Yeah, thank you for starting this activity that now draws so much attention and so many people together. All right, so let's get started with the technical program. So we start off with two keynotes from some of the strategic partners of the OpenAirInterface Alliance today. And it's my pleasure to introduce the first keynote speaker, Adrian Garcia-Rodriguez, from Ericsson France. So Ericsson has been a partner for many years of OpenAirInterface and joined the alliance officially a few years back. So Adrian is working with Ericsson in France in the newly founded research center in France. And he's the head of the artificial intelligence machine learning techniques for the radio. Adrian, he got many awards. He has already a very strong history. He has gotten an award. He got the Ericsson Impact Award. He has also, before working at Nokia, he has gotten the Bell Labs Island Certificate of Outstanding Achievements. He has filed many patents, and so it's our pleasure to welcome him here today. And he's going to talk about the road of artificial intelligence towards 6G air interface. Welcome.
Hi everyone, good morning. First of all, Christian, thank you for the engaging story. What a journey, really impressive. It's my pleasure to be here and now looking a little bit more into the future, talk to you about the road of artificial intelligence towards the 6G air interface. And I would like to start with a strong statement. AI/ML is a reality and will be happening in real RAN products. And to illustrate this, let me showcase how Ericsson products will be evolving in order to support AI/ML. To do this, let us take a look first at one of our current Ericsson RAN processors that has been built for 4G and 5G. If we open the box that you can see in the screen, you will find two processing components. The first one is Ericsson Silicon. This Ericsson Silicon has been built to execute the demanding layer 1 workloads, and it includes both accelerators and digital signal processors. If we keep digging, we will also find a board processor. This board processor has been dimensioned for executing the workloads of layers 2 and above. If we keep digging in this box, what we will find also is some memory-related components. We will find some dynamic storage, and we will find some persistent storage as well. Now, let us take a look at the next generation Ericsson RAN processor that has been built for 5G advanced and enhanced AI/ML. If we pay attention to the memory, we will find that now the dynamic memory components has been grown by a factor of approximately 3 times. And we will also notice that the persistent storage has been increased by approximately a factor of around 20 times. This is critical for executing AI/ML workloads because one could think of this dynamic storage as the storage where, say, the neural network weights will be loaded for inference. And the persistent storage can be seen as some sort of in-device model repository. But not only this, if one also pays attention to the processing components, we will find that the Ericsson Silicon has not only been dimensioned for executing RAN workloads, but also to execute specific AI inference workloads. We also have enhanced the board processor, which now includes the latest instruction set to accelerate the AI inference workloads. And at this point, I will understand if some of you are saying, but Adrian, why are you talking already about AI ML in 5P Advanced? And the reason for this partially lies on what's going on in the 3EPP right now. So I would like to spend just 5 minutes to briefly summarize what's going on in the standardization. So right now the 3EPP is working on release 19, and it is actually already specifying some AI ML related use cases for the air interface. The first one is AI ML based positioning. The key idea here is to develop an AI ML model that, in the simplest of cases, at the input will receive radio measurements, and at the output will produce the actual locations of the user. This AI ML model, depending on the specific use case, can be implemented at the UE, can be implemented at the location management function, or it can be implemented at the G0B. This figure illustrates, in essence, how this works. First, the user will send sounding reference signals to the radio units. These radio units will receive these signals and transmit them to the G0B, which will then execute an AI ML model that will help the location management function to determine the user location. This use case has been shown to be a game changer in terms of location accuracy, especially in those challenging non-line of sight environments, where it has been shown to improve the accuracy when compared to traditional algorithms by a factor of around 100 times. The second use case is AI ML-based bin management. And here the intuition is to reduce the overhead of the typical exhaustive bin search procedure that you can see in the slide. Depending on the variety, we have that the artificial intelligence model can be executed either at the UE or at the G0B. And the key intuition is to use a reduced number of measurements in order to determine which is the best beam that will be used subsequently for the communication. Performance-wise, this use case has been shown to provide throughput increases between 5 and 10% when compared to the exhaustive search that the 3EPP has considered as a benchmark. Internally, we have also run evaluations of this use case, and we have seen that there are limited gains when compared to more advanced schemes, like those included in Ericsson products. But the 3EPP is not only focusing on use cases. The 3EPP is also establishing overarching AI ML foundations in preparation for 6C. Concretely, the 3EPP is defining a future-proof functional framework that includes means and requirements for data collection, so that we can, say, train our AI ML models, and also is defining procedures so that we can manage the lifecycle of the UE models. You can see some examples of the procedures that are being defined in this diagram, which include model training, model storage, and model inference. Not only this, the 3EPP is also working on defining round 4 testing and model performance monitoring requirements, because we want to make sure that once these models are deployed in the field, they can interoperate when we have devices coming from different vendors and work well in the field. Now, let me connect the dots between the product and the standard. And to do this, I think it's always good to put ourselves in the shoes of what I think is one of the coolest jobs in the industry, a strategic product manager. So these strategic product managers, they have to essentially decide which is the roadmap of the future products and decide which features are implemented in our products or not. And now imagine a researcher comes to their table with a new fancy AI ML solution, asking them, hey, look, I have this fantastic approach. Why don't we implement it in our products? I think that most of us in this room will think as follows. First, we will say, of course, usually these strategic product managers are engineers. We want to implement the solution that provides us with the best performance. But at the same time, I think that if we were to be mindful, we will think twice and only implement those solutions that guarantee that the complexity, the energy, and the cost of our hardware remains competitive. And this is what we believe will continue happening with the AIML solutions. And it is not new. For us, communications engineers, we have come up with really advanced and high-performing solutions over many decades. And many of them, unfortunately, do not end up implementing our products just because the trade-off between performance, complexity, energy, and cost is just simply not favorable. Perhaps there is a key difference happening with the AIML, which is that the field is really moving at a lightning speed. And that complicates the job of us researchers and strategic product managers, because we really need to be on top of our game and make sure that we're tracking all the progress that is happening. Let me illustrate to you an example of the cutting-edge research that we are currently developing at Ericsson Research for ready applications. To the right, you can see an example of a neuromorphic neural network for a ready application, in this case, channel estimation. These neuromorphic neural networks, they have a particular property that makes them very appealing for radio, which is that only neurons that are active during an inference pass require processing and consume power. You can see those active neurons highlighted in white at the top figure, and the number and the percentage of active neurons across time with different inferences at the bottom part. This is more powerful than, say, the typical static sparsification techniques that just remove weights or neurons in a given architecture. But it comes at a cost, because training is more difficult. Now, let us put ourselves in the shoes of this strategic product manager. If we're coming up with these solutions, rapid development and testing becomes essential. And this is where we can draw an immediate connection between AIML for their interface and the OpenAirInterface work. We believe that AIML advances will be boosted by a full stack network emulation. And this is very intuitive, because AIML is a data-driven approach, which means that our solutions will be as good as our data. And when they are deployed in the field, they will be as good as the training data we use was as close to the field as possible. So here we believe that OpenAI interface-based digital twins are a key enabler to both perform accurate AIML evaluations of our features and also to generate data that can be used for training. And at this point, I will understand also if some of you may be saying, but why is this particularly relevant now? So let me explain just very briefly what is our Ericsson projection for the upcoming 3GPP and productification of 6G. Let's start with 5G Advanced. Right now, the 3GPP is working on release 19, which will finish around 2025 and will be followed by still another 5G Advanced release, release 20, which should finish by the beginning of 2027. Actually, this week, there was something important happening in 3GPP, which is that there was a RAN plenary meeting. I was actually in a 3GPP meeting 3 weeks ago, and it was a fun exercise because there are some use cases that I didn't mention before, where we are still studying whether to specify or not, especially those related to the acquisition of channel state information at the base station. And this week, there was a decision to understand what to do with them. So actually, there will be an additional use case being specified in release 19, that is the UE-sided CSI prediction, where UEs will implement an AIML model to predict the evolution of the wireless channel in time and report that back to the base station. And there has been a use case which is quite intricate and that has been studied for more than 2.5 years now, and that will continue to be studied, which is a two-sided CSI compression, where there is a split model between the base station and the UE. And the idea is that the encoder part of an AIML model at the UE will compress the information that will have to be decoded by the decoded part of an AIML model implemented at the G0B. As you can imagine, this is quite a difficult use case to standardize, and it's the first two-sided model that the 3EPP is considering. And we will continue to study it because we still haven't resolved all the interoperability aspects that we need to address. Now, let me shift gears and move on to 6E. For 6E, we know that the study item will start at the beginning of 2025 and will last approximately 21 months, meaning that it will finish around the middle of 2027. The first work item that will provide the first 6E specifications will immediately follow, but we don't have a timeline agreed yet. We do have, however, the point in time at which we will agree on this timeline, which is in the middle of 2026. Considering this, we expect to see the first commercial 6E systems around 2030, that is more or less 10 years after the first 5G systems appear in the market. So what is the role of AIML in the 6E air interface? Well, we believe that 6E will include use cases, and we believe that 6E should focus on those use cases that are capable of demonstrating meaningful performance gains against competitive benchmarks. And the last part of this sentence is really crucial. And I would like to dedicate the next few slides to talk about how do we measure and how do we make sure that the AIML solutions are compared in a fair manner against non-AIML model-based solutions. And to do this, I think it's good that we put ourselves again in the shoes of a strategic product manager and we focus on a specific feature. Say, for example, AIML based on SRSs performing a channel estimation and a prediction. You can see this use case highlighted in the block diagram at the bottom of the slide, where we have a transmitter to the left. In this case, it will be a UE. And we have a receiver to the right. In this case, it will be a base station. And as part of the receive processing, we take the SRSs. And now, instead of performing a conventional channel estimation solution, we implement an AIML approach. The key message that we would like to convey is that comparing against high-quality benchmarks is essential if we are to draw the right conclusions and determine which are the relevant 6E use cases. If we are good strategic product managers, what we would ask is to compare with near product solutions at the very least. So this means that we have two alternatives to compare. The first one is an AIML-based alternative, where a UE sends first an uplink sounding reference signal to the base station. The base station will execute an AIML model that will perform a channel estimation and a prediction of the evolution of the wireless channel. And if we are in a system where the uplink and downlink channels are similar or reciprocal, like in time division duplex systems, we can then use this information in order to pre-code or be informed towards the UE. One would expect that we compare this solution with something that resembles our current products. Again, the UE will send an uplink sounding reference signal. The base station will implement a model-based solution, and the output of this model-based solution with the channel prediction or estimation will be used to pre-code or be informed towards the UE. Let me tell you something. The channel estimator that we have in our products is quite advanced. It's comprised of a variety of sub-blocks, and it is resembling nothing the usual linear channel estimators that we can see in the literature, like least squares or linear MMSE. And I argue that we should be comparing against these baselines. And I would say that the vast majority of my time since I joined Ericsson has been spent on comparing against solutions that our top engineers have been developing over many years. And they always say when we present them with an AI/ML approach, oh, but have you compared with this very smart solution that this engineer came up with? And I think it is fair. Another key lesson that I have, and we have learned the hard way. Sometimes, just because we try to do fast evaluations or come up with quick conclusions, we use intermediate performance metrics as our key performance indicator. In the case of channel estimation, one could think as, say, a typical one, the mean square error between the prediction produced by, or the estimation produced by the algorithm, and the real channel. And I tell you, these metrics, sometimes they are useful, many times they can be deceiving. We have seen amazing improvements in intermediate metrics that then they just simply do not translate when we focus on our final metric of interest, which is typically downlink throughput in this use case, or the delay. So with this in mind, if we are good strategic product managers, we will want to see this in a real setup with real data at the very least. And so this is what we did. And so I'm just going to show to you one result today because I don't have that much time to go through the entire chain of results. But what we did was basically we performed a measurement campaign and we measured channels that then we integrated into a product grade simulator to evaluate the downlink throughputs obtained with a variety of channel estimation techniques. And by injecting artificial noise, different signal to noise ratios. You can see the map of where these measurements took place to the right-hand side of the screen. This is actually the Ericsson headquarters in Stockholm, is in Kista. What we did here was we have a massive MIMO base station with 64 antennas, which you can see at the bottom left of the figure. And this massive MIMO base station was communicating with a UE that followed the route that you can see highlighted. For this particular route, we did many routes. It took approximately around 10 minutes. And with an SRS periodicity of 5 milliseconds, we collected around 120,000 SRS samples. Let's see what happens with the results. But before that, let me just highlight that we have regions with both line of sight and non-line of sight. And since we are following a data-driven approach, we can also have some fun and start training our algorithms with the data collected from the measurements and see what happens. In this particular case, what we did was to split the route into two regions. One region, which is highlighted in dark blue, where we collected data for training our AI/ML models, and another region collected that you can see highlighted in light blue, which is the area where we will evaluate the performance of the different AI/ML solutions. Let's take a look at the results now. To the right, you can see a curve, a plot that illustrates the throughput evolution with time in that light blue region. There are 4 schemes being compared there, so let us go one by one. To the top, we have the solid green curve. As I mentioned, we are using a product grade simulator, which means that we can cheat and see what would happen if we had ideal channel estimation. So this is our upper bound. And we find it is actually quite important to always understand what is our upper bound. Because as you can imagine, we have evaluated a large number of use cases, not only SRS-based channel estimation. And we find that in many cases, the gap between the ideal and our current algorithms is just simply too small for AI/ML or any other algorithm to provide any meaningful gain. Those we shouldn't be worrying about. If we look at the 2 bottom curves, we will find 2 overlapping ones. A dash red, that is something that resembles what is implemented in our products. It's not exactly the same. And we also have an AI/ML-based solution that actually has been trained with synthetic data. So for those of you familiar with the 3PP channel models, what we did here was to simply take the 3PP urban macro channel model, deploy a large number of users, channel realizations, inject noise and interference, and train an AI/ML algorithm capable of knowing the real channel, denoising, and predicting. Something that I find not obvious is that even when trained with synthetic data, the performance of the AI/ML-based solution did not collapse. I mean, of course, we're not improving with respect to the baseline, but to me, it is quite meaningful already to see that, hey, it's learning something with synthetic data, and then even when exposed to real data, it performs relatively well. We and others have already seen this. If we continue moving up, we will see that the dotted blue curve, which is the AI/ML solution trained with real data, is the one closest to the ideal performance. And the conclusion that we can make based on this and other use cases that I'm not showing to you today is that actually using real-world data for AI/ML training generally makes a positive difference. This is not straightforward. The amount of useful real data will depend on the use case. We see use cases that are highly dependent on the specific product implementation or specific on the specific channel distribution will benefit from using more real data than others where literally there is very little impact of the channel or of the product. As you can imagine, we are still working on this, and there is a lot of work for us to be done. For example, we are still, as an industry, I think, lacking to understand what happens when we integrate multiple functionalities, especially if these AI/ML functionalities interact with each other. Say, for example, we implement this AI/ML-based SRS, channel estimation and prediction, and we combine them with an AI/ML-based receiver. It's not immediately clear that the gains that we see separately will become additive. We need to understand this. Something that we and others are also still, I believe, lacking systematic analysis is what happens when we overfit our AI/ML models to specific devices and to specific sites. And notice the mindset here. This is slightly different. Typically, we have developed algorithms so that they work well everywhere, wherever we deploy them. But now with AI/ML, the story is changing because, say, we know that we are going to deploy these algorithms in a specific base station that is deployed in a specific site that will experience certain channel conditions. So it's not straightforward to say that if we tailor our algorithms to these specific conditions, the performance will not improve. And this is where we believe that digital twins and site-specific AI/ML go hand in hand. The video that you can see now to the right is actually a digital twin representation of exactly the same location where we took the real measurements. And this is quite attractive for us because instead of having to take some engineers, drive a van, create the equipment, and all the costs associated with it, we can just, as long as we have an accurate digital twin, simulate this. And notice that this is a real digital twin, as I will explain later. This is happening a full stack in real time. And what we can do with this is we can collect data, as I mentioned before, for training, and we can use this to evaluate the performance of our algorithms when deployed in specific sites. We think that this is necessary if we are to develop product-grade AI/ML interfaces. We are not there yet. The industry, we believe, is not there yet. We need to make sure that AI/ML generalizes and is robust when exposed to different products and system configurations. Different antenna geometries, different bandwidths, different number of users, different reference signal patterns. The list goes and goes. We still have some work to do before we make sure that AI/ML solutions work well in the typical dense multi-cell setups with massive antenna arrays performing multi-user MIMO. This is where we believe that digital twins can make a difference. To the right, you can see an illustration of the digital twin that we have been working on in Ericsson for a number of years now. In particular, you can see the rendering and the mobility parts of our digital twin, which provides a cloud-native, full-stack network emulation in real time. The antenna that you can see in the product is actually an Ericsson radio. And what you can see in the video as well is that we have several of them deployed. You can see in an illustrative manner our ray tracing capabilities. You can see the rays between those base stations and the users. What this allows us to do is to perform evaluations for AI/ML as close as possible to reality. We can have our users, which you will see next, moving around the scenario, and we will be able to actually see what happens with their signal, which is what we most worry about in the physical layer, and collect data to train our AI/ML models. The key idea behind our digital twin is we want to design high fidelity emulators of the radio units, the radio environment, the mobility, the radio propagation, the UEs, so that from the perspective of a real network stack, they are indistinguishable. Let me illustrate to you what is going on here behind this very cool video. I guess that some of you may have seen this picture. What's happening here is, to the left, we have, starting from the left, we have a full NR network stack above the low layer split. This full NR network stack is working both with the OpenAirInterface components in some setups, and also with Ericsson commercial stack. We have everything. We have the packet core, we have the operation support system, we have the central units, we have the distributed units. In the middle, what we have is our directional radio model and channel emulator. And these are the components that I was mentioning before. Here we have the radio units, we have Ericsson propagation model with ray tracing, and we have a Godot-based game engine that drives the mobility of that mannequin that you saw moving before in our digital twin. To the right, this mannequin is actually literally wearing a UE. Now, this UE, as you saw, we have several of them in our scenario, and we have implemented the physical layer of these UEs, and we're also using the OpenAirInterface, depending on the setup, either for also this physical layer or for implementing the layer 2 and 3. Remember, this is running in real time. Let me just show you a video with an example where we are actually running Ericsson's commercial stack with an OpenAirInterface UE. In this simplified scenario, this is again Ericsson's campus in Kista, in Stockholm. What we can see to the left is how the RSSI, the received signal strength indicator, varies as the user moves closer and farther from the base station. You can also see the traces of the amount of data being received by the UE. In this case, we're sending simply UDP traffic towards this UE in downlink. And as you will see, as the UE moves, our real-time engine with a ray tracing propagation model is recomputing the wireless channel evolution. And we will see how the throughput drops as soon as the user crosses through this brown building that will pose an obstacle. For this particular video, we are using the layer 2 and layer 3 from the OpenAirInterface stack. You will notice how the throughput went from around 350 megabits per second to around 150 megabits per second due to the blockage. Now, we are grateful for having the possibility of using OpenAirInterface to have this type of capabilities, and we also want to contribute to the community. That is why we are planning to open source the mobility and the visualization front-end app of the Godot engine that you just saw. This Godot engine that has been used to build these two components actually has a quite forgiving MIT license. And what we're hoping to achieve with this is we would like that we can define propagation path APIs, for example, towards the OpenAirInterface RF stream. And we would like to develop an RF propagation model that can be used by the community and perform these kind of experiments that we were just showing. We are currently working on the FOSS release process, and I think our Ericsson colleagues in Sweden will be able to tell you more details about this. Let me conclude with the key takeaways from this talk. A question that I hope some of you may have posed before this presentation is, why are we even working on AI/ML for the air interface? Especially if you believe that conventional algorithms already provide us with close to optimal performance. Well, there are two key reasons that we have discussed. The first one is, we are engineers. We always like to investigate if there is a solution that can make us closer to the ideal. Here, our current view is that we have evaluated a large variety of use cases, and except for positioning, we have not found a game changer for typical setups when compared against competitive benchmarks. Typically, for most of the use cases, we see performance gains that range between 5 and 10% when we focus on the ultimate metric of interest, which is the downlink throughput in most of the cases. Of course, I am not going to be brave enough to tell you this is the definitive answer. No. There is still lots of work ahead to answer this question definitely, and as you saw before, we need to understand what happens when we start combining multiple AI/ML functionalities, when we start understanding site-specific models, or when we go to bigger systems in more realistic conditions. This is work in progress. At the same time, we also discussed a second key reason is that the AI/ML world is evolving so fast and coming up with new AI/ML architectures and new hardware accelerators that we need to be really closely paying attention to understand what is the progress, what is the cost, and whether it will be worth for us to integrate at least some of these accelerators in our hardware. We also discussed how we are going to standardize and implement AI/ML. We saw that 5G Advanced is just starting to implement AI/ML for their interface use cases, and that is defining an overall framework that can be used as a basis for 6G as well. Most importantly, in the standard, we are to make sure that different vendors interoperate with each other and that the solutions that we implement, they work well in the field. And that is why we are also trying to develop a robust testing and monitoring framework for AI/ML solutions. We also discussed how data collection and performance evaluations are really important. And I just showed you a glimpse, but we, in other use cases and other companies, are already showing that using real-world data is important, at least for some use cases. And a key enabler here is the digital twins, because we cannot expect, at least at an early stage, that we go and perform the type of measurements that I showed you at the beginning to collect real data. We need to rely on easier and cheaper solutions, and that scale better. Digital twins are an enabler. And that brings me immediately to the role of the OpenAirInterface, the digital twins, and AI/ML. At least for us, the OpenAirInterface is central to develop accurate digital twins. You saw we are using the OpenAirInterface L2, L3 UE so that we can run our digital twin in real time. And here I would like to convey two messages. The first one is we are delighted to be on board the OpenAirInterface. This would not be possible without that. The second one is that we are highly appreciative of the OpenAirInterface, not only because of the technical leadership, but also because of the profound understanding of the commercial realities that companies that implement 3GPP-based systems or that work in the 3GPP standard face. And proof of this is the long-standing license that the OpenAirInterface has had and has proven to withstand the the phase of time. We are working also towards open sourcing the rendering and mobility components of our digital twin, and hoping that that serves as a boost for the entire community in order to evaluate AI/ML or other types of solutions in the future with digital twins. All in all, we believe that there is a long road ahead for AI/ML for the air interface before we can figure out and make sure that these solutions work well in the field. And we believe that all of us here and our community needs to keep working together to make sure that 6C makes the difference we are all striving for. Thank you so much.
Adrian, thank you so much. That was a great presentation, and I think it's a very big recognition for OpenAirInterface that you've integrated that into your products, into your digital twin, and I think it's a great recognition for the license of OpenAir and everything Christian and Raymond you have started. Thank you so much. We have time for one or two questions. Is there any from the audience?
Okay, thank you for the presentation, really insightful. I wanted to ask one question related to the ray tracing capabilities that you're using. Have you made a fair comparison between Godot and NVIDIA Sionna, for instance, for using your AI/ML models and?
So, this is a great question. Let me start with Sionna first. So Sionna, for those of you that are not familiar with it, is an open source tool and simulator that has been developed by NVIDIA. And it's a great tool. It can be used for training and evaluating the performance of many AI/ML models. To my knowledge, I am not working with the ray tracing capabilities of our internal ray tracer. I don't think we have compared it. So I cannot say whether what the conclusion of that comparison would be. What I can say is we're pretty confident because this ray tracer has been evaluated over and developed over a large number of years and tested against real measurements, is that we are pretty accurate. My understanding is that the ray tracer from Sionna is still under development and some of the key propagation mechanisms are still not there. It is likely that we'll continue progressing, but as of now, we are quite comfortable and I would say quite proud of our ray tracing capabilities.
Okay, so what you have shown is not using at all NVIDIA Sionna?
No.
Okay.
We are using our own internal ray tracing capabilities.
Okay, thanks a lot.
Just curious about the role that you mentioned open source for OAI plays, like compared to, because you're Ericsson, right? You have access to your internal code. So is the benefit in terms of some of the exploratory features and also the contribution from the other organizations in the community?
Yeah, I'm sorry, I didn't get exactly.
Yeah, so the question is, for example, for companies like Ericsson, right? What's the main benefit of using open source versus your own closed source systems for your own internal research?
Right. This is a big question. I can give you my answer, my personal view on this. I think that when you release something to the community, it's a great way of, especially if it's a topic of interest, like say digital twins, it's a great way of boosting the entire knowledge and raising awareness of a specific topic. The technical depth will grow just because there will be so many people working on it. At the same time, we are a business and there are some components that in some cases we prefer to remain proprietary because it's part of our key business. We think that this is a game where we can both give, like we are saying we want to give at least some parts for the community to grow, but other parts it makes sense that we also take, like the OpenAirInterface UI. It's a game where ideally there will be a fine balance and that allows both commercial opportunities for companies like Ericsson or others, and at the same time that the community can also grow simultaneously.
Let's thank Adrian once more. Bill.